Hi, today we start chapter 3, which is about sets. We have a couple of goals, or a few goals in this chapter. Number one is to become familiar with this notion, that's fundamental notion in the world of mathematics. And the other one is also to practice proofs on sets, where we'll actually practice what we learned in first two chapters. At the end is probably the most important section of the whole chapter, which is 3.6, which is the method of mathematical induction. That's very important for all kinds of mathematical applications and proofs, basically. And for example, will definitely show up on one of your quizzes, on exams, and so on. Our goal today is fairly limited, so we just do the introduction into the chapter. So our section is 3.1, basic definitions of set theory. Basic definitions of set theory. So we have a couple of goals. First, to see what are sets. And sets are so much fundamental on the basic level of mathematics that there is no definition of sets, because any attempt to define sets would actually use something that's simpler than sets, but there's nothing simpler than sets. So what is it? I can just share with you what is our intuition about sets, and that's the only thing. We don't introduce them formally here in this course. But our intuition about sets is these are the objects that only care about the membership. So when I say, so I'm happy and my set is described, so let's say set A, when I can list the elements, let's say 1, 3, 7. And this is a standard notation. We open the curly brackets, we list the elements that are inside, we finish the curly brackets. And then as long as the description definitely can answer the question, is someone in or out, then we are happy with the definition of set. So for example here, obviously for my description 5 is not in there, but 3 is, and so on. Sometimes things are a little bit described in a little trickier way, so it's not always so easy to see who's in and who's not, but let's postpone that for a moment. And so in the beginning we talk about the way we define sets. Let's look at the following set example. Let's set A again, I'll call it A, I can use the other names. And then I will use something that you already saw in your basic math class, it's called set builder notation. So what would that be? You take one set that you already know, I'll take integers, and I'll say the following: set of all x is from Z. So this is membership relation. So element belongs to a set. I already used it before, so I'm not introducing it here as a new notation. So generally I say x belongs to Z, and then I will list all the elements from Z that have certain property. Let's say that x is even. So here, or sometimes when we are a little more kind of conservative in what we accept on the left side, we'll just give them the name x, and then after the line we'll explain everything. X is in Z and x is even. So we hope that this description precisely describes who's in there. So generally one would say what? That 2 is there, 4 is there, 6 is there, although this set is infinite, and of course I cannot list all the members. I lost 0, minus 2, and so on. So here we have a description that's equally good as it is this listing. Actually this one is more precise because we can never really list all the members. Here's another example. Set of all x's from Z such that x squared is less than negative 1. Or equal to negative 1. Why am I making it more complicated? what can you say about, so here it is. We know what Z is. Here is a fine, nicely described property. So this is really a set. Let me call it A. But what's interesting about this set, that there is no integer such that A squared, integer A, such that A squared is -1. So generally, this is the set with no members. Those sets are called empty set. And here is the notation. Zero cross in mathematics is used to label that empty set. So what is empty set? Set without members. One would say, why would we need such a set if there's nobody in there? It's just good for algebraic properties of sets, and sometimes it's useful to think of it as an object. Like, for example, in computer science also, when you have strings and then you want to join strings together, sometimes say, oh, I'm joining empty string, and that's absolutely acceptable and, as I said, sometimes convenient, so that we don't need to avoid those sets. So here are a few examples of sets. As I said, basically everything that can nicely describe all the members is considered as a good definition of a set. And then once we know what sets are, at least intuitively, we are asking a few important questions. So first question is always about equality of objects. So equality of sets. And you will see, we'll talk about this one more in section 3.2. We'll do many proofs about how to show the two sets are equal, but here let me just put a definition. So sets A and B are equal, and that's by definition, so this is, we are describing law of the land. When will I accept that two sets are equal? If and only if they have the same members. So that's what I have. They have the same members. And then that's, of course, a decent sentence in English, if not nice, but we would like something that's more formal in the language that we developed in the first two chapters. So what does it mean that they have the same members? That for every x, if x belongs to A, it also belongs to B, and the other way around, so that's equivalent. So that means every x, it's either in both of them or out of both of them, and that's, I would say, a reasonable way to define when are two sets equal. And one more definition, when do we say that set A is subset of B, then we'll say again, sorry, this is here, by definition, another here. By definition, that means that for every x, if x belongs to A, then x belongs to B. So that means if all the members of A are members of B, but it doesn't have to be the other way. For example, that's why here, I don't know, California is subset of United States. California meaning what? Like, let's say, land-wise or population-wise. So something like that. All right, so we'll talk about how do we prove that things are equal or subset of each other in section 2. But here's one nice example to illustrate all of this. So this is example 315. And something, variation of this example very often shows up on the exams. So case, set of all x's from Z such that 2 divides into x. K is actually a set of all even numbers. L is set of all x from Z such that 3 divides into x. And then M, set of all x from Z such that 6 divides into x. So the question is, what can we say about the way these sets are related? Can we say that they are, some of them are equal, or some of them are subset of one another, and so on? So let me illustrate at least first attempt at the techniques of showing that things are equal or not. So for example, what can I say about K and L? So question, is K equals to L, yes or no? The answer is no. Why? I will find counterexample, because this is universal statement. So if I find counterexample, that means that someone belongs to one of them and not to the other one, then they are not equal. So here it is, so let me take number 3. 3 does not belong to K because 3 is not even, but 3 does belong to L, so here it is. 3 is witness to the fact that they're not equal sets. Alright, so L has some elements that K does not have, so I can relax the question. I say, alright, is L bigger? Is K maybe subset of L? Because L is obviously not subset of K, because some elements of L are not in K. Is it this way? No, it's not, because now what? I'll take, let's say, 4. 4 belongs to K, but 4 does not belong to L. So basically these two sets are kind of not comparable. Very often to see relations between the sets we use so-called Venn diagrams. So in this situation, when two sets are not a subset of each other, then we usually draw them like this. K is this, L is this. It's a generic situation. They have something in common, and then some pieces are stemming from one another. They are not subset of each other. But let me ask about M. So now, I need a little space here. Let me try to squeeze it in here. I hope you will be able to see. I want you to have them all on the same page. So my question is M subset of K? So that means, is every element of M element of K? And the answer is yes. I will not insist on precise writing, as I said, that's for chapter 2, but the answer is what? How do we prove that? Let X belong to M. That means that 6 divides X. So that means that X equals 6K for K and Z, but that's equal 2 times 3K. So 2 divides into X, so X belongs to K. But in the same way, I can for the same X write 3 times 2K, so X belongs to L. So so actually what we see here, that M is subset of K, but M is also subset of L. Obviously, it's not equal to any of them. It's just what we say, proper subset. So that's the introductory story about how do you test if something is equal, how do you test that something is a subset. So once again, to prove that it's subset, you need to pick arbitrary element from one of them and show a reason why it has to belong to the other one. To show that it does not belong, that one set is not subset of the other one. You just need to find one counterexample, and that's it. So that's first thing. Second thing that's important, and you are all familiar with it, you have it in some basic math courses, and that is some operations among the sets. And generally you need to memorize them because we use them frequently in mathematics, and also here we'll use them to exercise some operations. So what will that be? What is the intersection B? This is a set of elements X, such that X belongs to both of them. So you see, you saw this in your basic math courses, but here we have now language to express this precisely. Venn diagram says, if this is A and this is B, this is their intersection. What about A union B? That set of X is to belong to one of them. And you will see in our proofs that connection between logical connectives and operations will be very important. So in this case, it would be, if this is A and this is B, A union B would be all this. So something that's covered by one of them or by both of them. So it doesn't matter. This is not exclusive, or you remember that from before. Let me just make this a little bigger. Or what else? We have A set minus B. What is that? That set of all x is such that x belongs to A and x does not belong to B. So what would that be? Here is A, here is B. So it must be within A, but with outside of B. Obviously, that's this. This is called set difference. It's not subtracting, set difference. What else? Sometimes, even if it's not explicitly mentioned, we often think about the universal set. What is that? For example, framework where we work, or where we are working. So for example, let's say U is universal set. Let's say, for example, it could be, as I said, it changes. You have to specify it, but you are kind of keep it in the context. So let's say our universal set is reals. Or it could be something else. Then suppose that I have the set A, let's say interval 0, 1. Then what do I mean by A complement? So complement of 0, 1. That set of all x's from where? From the universe, from reals. You don't even have to specify it, such that x does not belong to 0, 1. Basically, complement is nothing else but universal minus A. So complement implicitly assumes a universal set, and as I said, that should be clear from the context. And if that universal set changes, then your answer, what is a complement, changes. So this is like something that that we use very often, and that you should be familiar with, and then just do the homework about it. So this is just a fixed notation. Then again, some notation. When do we say the two sets are disjoint? That's a definition, basically. That means, by definition, that they have no common elements. Or that means if their intersection is empty. Or you can say what? Or you can say the following: it's not true that there exists x that belongs to both of them. So it's not true that they have element in common. So this is, I would say, these are standard notations used very often around sets. They use it in calculus, in other math disciplines. So I thought it's very important that we are aware of those and use them freely. Actually, because they go to slightly more exotic, not exotic, but maybe less frequently used notation, let me make it sure that I emphasize this enough. So generally, when element belongs to a set, so let's say 1 belongs, so this is the symbol for belonging to 1, 2, 3. So this is the symbol called belongs. So it says that an object belongs to a set that is listed among the elements. So that's why I thought I better emphasize it, because I started to use it freely, and I don't know how much I emphasized it. All right, and then three more notations actually. What would that be? I erase this now to have the whole board for new notations. So here it is. Ordered pair. So ordered pair, so again, that's a definition basically. If A and B are objects, then ordered pair will write like this. Be careful, these are parentheses, so they are not curly brackets. So ordered paired in mathematics is the object such that object with the property that A belongs to it, B belongs to it, and order matters, who's first, who's second. So that means the only thing about, so we think of it like two objects, but they are only equal if this is true. So whenever I write that AB equals CD, then it's not only the same content, but also who is first. First one is equal to first one, second one, so that means A equals C and B equals D. In the homework you will see one problem where you will be asked to describe that. I said here object, but I'm not saying, I didn't say how to construct it. So basically, how do you construct that? One famous so-called Polish definition was offered in your homework, and then that definition you're asked to show that it has this property. It's a little tricky, but just for those that really need to see objects constructed and not just assume that something like that exists. What else? New definition. If I have A and B to be sets, what is A cross B? That is, it's called direct product. It's set of all the pairs, A and B, such that A is picked from A and B is picked from B. So that's the definition. So for example, whatever A is 1, 2, if A is, for example, 1, 2, and B is ABC, then what is A cross B? You need to try all the pairs, but the first component has to be from A, second from B. So here is the easiest way. Keep first component to be 1, and then join whatever second component you can make. So of course 1A is the first one, then 1B, 1C. I exhausted all the options for my second component. And then I advance and I say 2, and then the same thing, 2A, 2B, 2C. And of course, if this one has 2 elements, this one has 3 elements, their direct product has, or cross product, has 6 elements. So this is because, so see, this is standard notation, A cross B. This is standard notation about the ordered pair. So ordered pair, I can say the name, ordered pair. All right, and finally, I want to mention one more definition, and that's basically it. All these definitions and kind of fixing the language for this section. So what is the definition? What's power set of A? This is like sometimes people write cursive P, although very often you'll see, and that's what I get, and then now it's like P, capital P of A. What is this? This is the following. This is set of all the subsets. So this is set of all B, such that B is subset of A. So you basically list all the subsets of your set A. And do I have example here? So this is called power set, yeah, power set. So example, basically, I'm gonna write it here again to have more space. So an example, let's say A is 1, 2, 3. So how would you write power set of A? you have to be careful to really take all the subsets so that you don't miss some of them, or so that you don't repeat the others. The safest way, although we'll learn even better strategies, the safest way is just to make it sure to actually go by size. So what? How many number of elements? So number of elements, it could be 0 element subsets, it could be 1 element subset, 2 element subsets, and 3 element subsets. So let me list them. So here it is. Every set is the listing, and then every subset will have its own brackets. So one subset with 0 element, that's empty. So empty is one of them. That one with 1 element, each of them has curly brackets. I need to list one thing. What could that be? It could be 1. Or next one is 2. And next one is what? 3. So here they are. So far I have 4 subsets. 1 is empty, and 3 of them are tiny. Now a little thicker, 2 elements. Who are they? Actually, you can think of it this way. If I take 2 elements, that means I'm just skipping one of them. So maybe order them how you skip it, or whatever your system is. So I'll take 1 and 2 and skip 3. Content is blank. So here's your next one. Then next one is what? 1, 3. Next one is 2, 3. Those are the 2 elements. I have to erase this to make more space. And then with 3 elements, that means take everything. 1, 2, 3. And then those black curly brackets should be finished. And that's it. So that's power set. And then you can notice one thing. That's what? A has 3 elements. Power set of A has, if you count 1, 2, 3, 4, 5, 6, 7, 8 elements, which is 8 is 2 to the 3rd. Can we make a rule? Can we guess a rule? So that's basically what we wanted in this section. As I said, it's a fairly simple section. So what are your goals? Let me summarize them once again. To know what is set. What is a set? Equal and subset. Operations, intersection, union, set difference, and complement. And then what do we want? Pair. We want A cross B. And we want power set of A. So here is the summary of everything we did today.